Well, good morning, everyone. Thank you for being here. It's my real pleasure to be here, and I appreciate the invitation very much. I'm going to talk to you today about a presentation that I gave about 6 months ago or so, first at NASA Goddard, which was, in a sense, an expression of where I saw some challenges in aerosol and climate modeling, as well as my frustration with the perception of the state of the science by some other scientists, some good friends, actually, and I'll tell you more about that in a few minutes. Can I just make sure, if I hold the mic like this, is this good enough so people can hear me? Okay, so I'd like to begin by thanking all of my contributors here. You can see that there are a lot of them who I'm at a level now where I don't get to do as much science as I like, and so I depend very much on other people helping me and working with me on these. And in particular, I'll note Po-Loon Ma, who's in the audience, and you'll hear from in a couple of minutes. It's been a pleasure working with all of them. So I'm going to begin by reminding you of this very well-known figure from the recent IPCC report, and just point out to you that in spite of progress, aerosols and their precursors remain an area of climate research in which aerosols are perceived as being extremely strong forcing agents in the climate system, but they also have huge uncertainties with them. And it's interesting to ask the question, how have these estimates changed since the previous IPCC? And you'll see that there have been some small changes, changes in aerosols and for AR4 and AR5. And you'll see that there have been some small changes. There are changes in greenhouse gases. Our knowledge, to be brief in summarizing it, is that the knowledge hasn't changed a whole lot, but we do have a better characterization of the increasing concentrations that we're seeing as well. So when you try and break down what's contributing to the aerosol, to changing the aerosols in AR4 and AR5, there are a very elaborate set of definitions of the components of aerosol forcings, often called the direct and indirect effects. And if you begin to look at them in the direct effects, the small differences that you see are associated primarily with our characterization of black carbon. And Chen Wang may be talking about this. He's done a lot of work in this area, some of it with me as well today. IPCC report. What you're seeing here via the symbols are incarnations of various independent models. And in the lower panel here are the mean estimates from clustered in terms of their mean value. But in terms of the aerosol indirect effects, they're all over the map. And there are the effects can be broken down further into those associated with changes in our AR4 and AR5 results. And you'll see the spread in the models is about the same for AR4 and AR5. So the real difference is associated with, and I was on the chapter that reported these results in IPCC, is associated with expert judgment. So how can we put this into context? What does it mean for our understanding of climate? There's a very interesting commentary that appeared in Nature in 2013 with this title, Foreknowledge of the Past. And the perspective of this author was getting a better understanding of those effects might not be as useful as was thought. So how many people in the audience read this commentary? 1, 2, 3, 4. Not very many. Excellent Institute from Geology in Hamburg as well. And Bjorn has been pushing on this for a long time, and he and I have dozens of exchanges about this as well. And I'm going to spend a little time trying to tease apart the arguments that Bjorn's making, and then set of instruments out in the field. Since I showed you a picture of Bjorn, I'm going to show you a picture of myself as well. And this is me wearing a Rudolph the Red-Nosed Reindeer mask. And for those of you who are familiar with the since I showed you a picture of Bjorn, I'm going to show you a picture of myself as well. And this is me wearing a Rudolph the Red-Nosed Reindeer mask. And for those of you who are familiar with the United States and Europe, you might know this Christmas legend about a deer, a reindeer that had a red nose. And this is a Christmas picture with me and my daughter as well. So if I wanted to contrast the two, then you could also think that I'm learning from Bjorn. And just as, I don't know how many of you know this picture of God delivering knowledge to mankind from Michelangelo as well. So this may be Bjorn's attempt to deliver such a message to me as well. Bjorn was commenting about this paper by Ken Carslaw and radiative forcing, but really a lot of it stems from our uncertainties about natural aerosols also. That was the point of it. And that was the major point in it as well. And Ken attempted to quantify that. He did a really careful job of it, and a number of us have done this kind of work to do the decomposition. What he did here was to vary the emissions of various precursors to aerosols and then uncertain processes within the formulation of clouds and aerosols that are sensitive to uncertainties, and watt per meter squared to volcanic sulfur dioxide emissions with a very broad range of uncertainties, and tried to characterize the uncertainties associated with fossil fuel emissions of precursors of aerosols, and assigned much narrower uncertainties to it as well. So his conclusion after teasing out all of these uncertainties was that 45% of the uncertainty arises from natural emissions, 35% from anthropogenic characterization of what the impact of those uncertainties are. And he started by reminding the audience that the cloud condensation nuclei concentration is a function, has a which is a function of the aerosol number and mass decisions. Cloud drop number also goes up, and then the cloud albedo through the tuning effect or the aerosol effect is also very sensitive to cloud drop concentration amounts. So you get cloud albedo being very sensitive to cloud drop normalized anthropogenic emissions, and then reduce it to kind of a cartoon form here, giving the same amount of information. And in this also reduce it to kind of a cartoon form here, giving the same amount of information. And in this also Ken then noted that the sensitivity of cloud albedo to anthropogenic emission changes is much larger at low values of anthropogenic emissions than at high values of anthropogenic emissions. And this is much larger at low values of anthropogenic emissions than at high values of anthropogenic emissions. And this, from this remark, Bjorn then went on to make the statements that I've just mentioned to you, and many more, which I'm going to go through here in summary form. So this is my take on Bjorn's line of reasoning here. He called them the joker in the deck, and said that most of the uncertainties are associated with cloud affecting aerosols, and can really be attributed to uncertainties in the emission rates of aerosol precursors from natural sources. If one was to go back to this diagram, because the natural emissions form a much larger contributor to the background aerosol and background cloud drop number concentrations than current models are characterizing. Bjorn also felt that if there was an aerosol joker in the deck, it was probably played out a century ago, and it's really irrelevant to understanding present and future changes in global climate. And this was the sentence that kind of drove me nuts. So I'm going to try and remind you, the audience, of some of the other issues that weren't considered by Bjorn and weren't considered by, that drove me nuts. So I'm going to try and remind you, the audience, of some of the other issues that weren't considered by Bjorn and weren't considered by Ken in his studies as well. The issues that weren't considered by Bjorn and weren't considered by Ken in his studies as well. Bjorn also concluded that poorly constrained natural sources determine the Ken in his studies as well. Bjorn also concluded that poorly constrained natural sources determine the state of the pristine atmosphere and dominate uncertainties in estimates of radiation. Bjorn also concluded that poorly constrained natural sources determine the state of the pristine atmosphere and dominate uncertainties in estimates of radiative forcing. And he took that from these careful sources determine the state of the pristine atmosphere and dominate uncertainties in estimates of radiative forcing. And he took that from these carefully considered statements that Carslaw made, but I've used in estimates of radiative forcing. And he took that from these carefully considered statements that Carslaw made, but I feel it was a misunderstanding. Carefully considered statements that Carslaw made, but I feel it was a misunderstanding of some of the points Carslaw was making. But I feel it was a misunderstanding of some of the points Carslaw was making. And lastly, he also contended a misunderstanding of some of the points Carslaw was making. And lastly, he also contended that the present atmosphere. And lastly, he also contended that the present atmosphere should be quite well buffered against further changes in sources from tropospheric. Also contended that the present atmosphere should be quite well buffered against further changes in sources from tropospheric aerosols, and I'm not sure that's right as well, and I'll remind you of that. Atmosphere should be quite well buffered against further changes in sources from tropospheric aerosols, and I'm not sure that's right as well, and I'll remind you of that. The ultimate lessons to be learned in sources from tropospheric aerosols, and I'm not sure that's right as well, and I'll remind you of that. The ultimate lessons to be learned, and this was one of his concluding paragraphs, is a lack of understanding of basic processes, in fact clouds, is limiting progress in quantifying present and future changes in the Earth's climate. And he was urging the community to spend less time thinking about aerosols and spend more time thinking about the other components of the climate system. So I'll leave it to you to decide whether that's the right conclusion or not. So here's some of the things that I think we're missing from Bjorn's interpretation. First thing is that Ken was only considering uncertainties in the first aerosol direct effect. This is the one which we know will be the most sensitive. The aerosol indirect effect is the fact that the cloud number has a direct effect on the albedo. This is one which we know to be most sensitive to aerosol conditions. And we've known for decades that global models overestimate this aerosol direct effect. It's been recognized since Sergey Menin's work in 2000. He also neglected all effects of aerosols on ice and convective invigoration. He ignored the fact that by focusing only on present and future forcing, that in fact the lack of our understanding about how aerosols have affected us in the last century is having an impact on our ability to characterize the climate sensitivity for the models or the climate system. If we don't know how much aerosols have been acting as a cooling agent over the last century, we can't really characterize how much the CO2 has been acting to influence the warming of the atmosphere or the climate system, and how it would change if we were to remove some of that aerosol forcings. And lastly, I feel like that the fact that natural emissions are contributing a lot to the uncertainty, which I agree with, doesn't mean that anthropogenic emissions are unimportant. It just means we need to be better at characterizing natural emissions. And this is kind of a logical fallacy from my point of view, where you're arguing that A depends upon B and C, and if B is important, then C must be unimportant. And in this case, A is anthropogenic forcing, B is natural emissions, and C is anthropogenic emissions and process representation. So he was basically making this logic error from my point of view. So what in fact is going on in our current climate models, and what can we do to improve this characterization? That's the balance of my talk, and I'm going to spend some time on these three topics for the rest of the presentation. The first one is to remind you of a very nice study that was done by Zhang in 2007, in which that group attempted to decompose the aerosol, a set of aerosol surface measurements over many different places on the planet into organics, which is described by the green contributions in each of these pie charts, and dust, sea salt, and sulfate as well, comprising the other parts of this decomposition. And what you'll notice is that in polluted areas of the planet, and even some unpolluted areas, that the organics are playing a very big role, and we know they're very poorly treated in climate models. And we make comparisons to observational estimates of secondary organic aerosols, this ratio of measured secondary organic aerosol to the model secondary organic aerosols. We find that that ratio is typically, if the model agreed perfectly, they'd be on this one line. And the models are often 5 to 10 times too low in terms of the amount of organic aerosol that we're producing. And furthermore, the discrepancy increases with chemical age. So people have been puzzled about this and working hard on it for the last 5 years and more. And there are a variety of explanations for it, but one that's been done, well, I'll tell you more about one that's been done in my group in a few minutes, but also there are other people who have been working on it as well. And yeah, so I should have slides a bit out of order. It might help to switch them. I'll do this one as well now. One of the other things that people noticed is that anthropogenic emissions is capable of changing the yield of secondary organic aerosols as well, so from biogenic aerosols. So what we thought is that when you put pollution into the atmosphere, it can affect the production of natural emissions as well, and thus, in a sense, can help to amplify the role of the anthropogenic emissions also. So to return to my discussion about the uncertainties in organic aerosols, Manish Srivastava's been doing some really interesting work in my division on attempting to do better characterizations of this. And what he's noted is, and a few other scientists around the world have been noticing that the traditional modeling approach is to treat secondary organic aerosols as semi-volatile compounds. These aerosols, once they've condensed out, have a relatively low volatility or high volatility, and they evaporate relatively easily as well. And so the aerosols might form, but they'll disappear quite rapidly. But recent lab and measurement data is suggesting that secondary organic aerosol is evaporating orders of magnitude more slowly than this theoretical treatment assumes. And the suggestion is that the aerosol is really very highly viscous and non-volatile. So he's put together a different modeling paradigm where he's treating secondary organic aerosol as a non-volatile, tarry, glassy, semi-solid, and also treating the resulting degradation of the SOA precursors quite differently from the traditional formulations as well. And I don't have time to go through the theory of it with you really, but it will just to say that I just want to note that the change in the treatment of secondary organic aerosols has huge implications towards our perspective on the role of secondary organic aerosols. So this is showing you 4 different treatments. The standard semi-volatile treatment, which is used in our atmospheric model. A non-volatile treatment, including fragmentation, which is shown here, where the burdens are a factor of 3 higher and the lifetime of the aerosol a factor of 2 longer. And then some intermediate some other variants of these formulations. Now, I've talked to you a lot about the polluted regions, but organic aerosols are also quite important in the remote regions as well. And one of the other missing treatments for organic aerosols my group is also focusing on, and this is a paper which it's just been accepted actually by a postdoc of mine, Susanna Burrows, in which we're attempting to model the collection of organic compounds from in the sea surface as bubbles rise through the surface layer of the ocean. And when the bubble bursts, the organic compounds which collect on the surface of the air bubble and on the surface of the ocean, because these are surfactants, are subsequently released to the atmosphere in the form of small drops. And what we've shown in this paper is that this treatment can make a really significant difference in the perspective of what the contribution of organic compounds from sea spray is. And depending on the products, the organic products that you find in the near surface layer, you can get very different seasonal cycles of the organic compounds in the sea spray as well. And I show you in the lower panel here the correlations between chlorophyll A and submicron organic matter for a standard assumption for climate models, and one in which you do a different characterization of the compounds which are in the surface layer of the ocean. And the only message I want you to take away from here is that the correlations can be very different, and they're spatially dependent. So you get changes in the spatial distributions of the aerosol organic matter and also in the seasonal cycle of that organic matter. There are also known impacts of aerosols on convection, both in terms of invigoration of the convection, where you, if you have small drops that form in the presence of pollution, those drops can be carried more deeply into the convective updrafts, where they glaciate, and the latent heat of fusion can then act to change the cloud height. And this has been historically neglected in climate models, and it also can change the properties of the aerosols and the cloud drops and ice particles that detrain from the cloud updrafts. So I don't have time to go through that, but those invigoration effects have been seen in observations. Ilan Karen showed some of these observations in 2012, demonstrating that you could change pollution changes rain rates and can also change cloud depths. And in fact, the presence and absence of pollution can change the cloud fraction as well. And I won't take the time to go through this. I'd like you to just read the red sentence here. On average, as the aerosol optical depth goes up, the cloud fraction decreases as well, and that's what you see with these lines and the yellow shaded area itself. So we've been doing a lot of work in climate models to try and improve these things, and I'm just going to show you a couple of results this point in the game. One of them is some work done by Hai Long and this year, and published this as well. I won't talk about the second panel here, but the standard CAM5, I'm showing here the seasonal cycle of surface concentrations, black carbon. The standard CAM5 is about 3 orders of magnitude too low. High latitude Arctic surface measurements. We remove the aerosol much too efficiently, and also the seasonal cycle of it is wrong. And we've been working hard on reformulating the process which is responsible for convective transport and removal of carbonaceous and other kinds of aerosols. And we're now up to having the right seasonal cycle, and we're still at a factor of 2 too low. But these remaining discrepancies, I mean, there could be many reasons for it, but among them we suspect that some of the discrepancies are likely to be due to missing emissions of black carbon as well. Other aerosol species are also improved, but I won't take the time to talk to you about that. We've also been attempting to explore the role of resolution on aerosol distributions, and this is some work that Polun and I have been doing together, and I'm showing you here on the top panel aerosol burdens at a 2-degree, 200-kilometer resolution model, and then the same simulation that's done at a 1/4 degree. So there's about 100 times more grid points in this model than in this model. The meteorological component of the simulations has been constrained to agree quite closely. What you can see are many more filamentary structures that are present in the high resolution simulation. And the other thing I want you to note is that the aerosol concentrations at high latitudes are much higher at high resolution than at low resolution. And that's because the delivery and the scavenging mechanisms that are responsible for removal and transport of the aerosols can be quite different. The clouds tend not to be co-located with the aerosol plumes, and so there are paths that allow for aerosol to move poleward at high resolution that are not present at low resolution. And some of this can be explained by changes in the clouds and the precipitation distributions. And Polun will talk more about this in later this morning, I think. It also changes the susceptibility of clouds to aerosols. So, okay. It's not, I won't walk through this talk or this slide in any detail at all, but it's just to say I don't want to leave the impression that high resolution is the only way to improve some of the treatment of some of these things. What we've found is at low resolution, clouds tend to be too pervasive, and they don't, they drizzle often, and they don't turn on and off as frequently as one sees in the real world. It's possible to recalibrate low resolution models to remedy some of these problems. And in a study by Ben Yang and Wen Qian and I and others, we've shown that one can change the frequency of occurrence of precipitation events in ways that make it look much more like the observations, and it's possible to improve precipitation characteristics in low-resolution models when one pays attention to these things also. So now, having just given you kind of an overview of where I think we are, I'm going to go back and kind of tease out some of the things which I disagree with in terms of Bjorn's statements. Bjorn is pointing out that most of the uncertainty is associated with the aerosols from natural sources. I think those natural sources are incredibly important, but they're not the only things that are important. He felt that the aerosols were probably playing a role a century ago, and it's become irrelevant to understanding of present and future changes. I disagree strongly with this. It's very easy to find signatures of aerosol forcing even in today's present-day world. I think that there's probably very few places on the planet that are not being influenced by anthropogenic emissions at this point in the game. But nevertheless, whether you're in a moderately polluted region or a relatively pristine region, you can still see the effects of anthropogenic emissions in these regions. And we showed that in some of that work was shown, for example, in the studies by Ilan Karen. The disproportionate sensitivity of aerosol forcing to the background state of the pristine atmosphere suggests that the atmosphere is strongly buffered. That is, it's insensitive to changes in tropospheric aerosols. I don't think so. There's lots of evidence that you can see on local climate features. And this is a repeat of what I just said, I think. The ultimate lesson to be drawn is that a lack of understanding of basic processes is limiting progress. That I agree that's true. This fundamental understanding is critical. But if the suggestion is that refocusing research on these basic processes should take away resources from the study of aerosols and their impact on clouds and the climate system, I don't agree. We need fundamental processes, or fundamental understanding of basic processes of the atmosphere. We need those for aerosols and for clouds. And that's the end of my talk. So if there are questions, I'd be glad to take them. Thanks.
Thank you, Phil. So we still have quite some time for questions. Yes, Chen, please.
Was wonderful. Actually, part of my talk is also inspired by Bjorn's comment.
Yeah, Bjorn came and visited Chen's lab for a few weeks last summer. I think that
was amazing. But just to add to that, I got a chance to read Castle's paper in the early stage in a different journal. You know what that means? So there's a fundamental flaw in the methodology because they use a green function. I was basically just build an emulator, but for aerosol, probably use a green function. It's highly dangerous. People know that's had a bias in the distribution. So we at MIT we've done a lot of such things. We use a very different methodology. That was really actually one of the fundamental reasons. So they leading to some of these surprising results.
Well, one of the things which I find interesting is I remembered that he used Green's function analysis, but I think you can get some of the messages that Ken delivered from other analysis techniques too. And for example, Steve Gann did a nice study in that. Maybe you guys have also done it. So I think a variety of different analysis methods can be used to extract some of the information that Ken extracted and published in that paper. And if you actually disagree with things that he said, I'd be real interested to talk to you about that too. But so it may be that the methodology could be improved, but some of those messages, I think, you can get at it from a variety of different ways also.
Yeah, exactly.
I want to throw the aerosol climate connection in a different perspective. In the beginning, using the radio forcing, I have a strong opinion about that, including the ozones and the aerosols, primarily because of the regionality of that. The greenhouse warming caused by greenhouse gases basically is a global scale in the very long term, and they're forcing the climate. If you look at it from a scholastic point of view, so aerosol forcing basically is popping, the hot spots popping up and down.
Yeah.
So fundamentally, I think there's the aspect of the kind of feedback to the forcing, whether it's a uniform, homogeneous, or is a more sporadic one. And I was in China, in Beijing last week. I was lucky because the whole week was very clear. I see the sunshine and also the moon in the night. So the reason for that is because of meteorology, the wipeout of the air pollution. So what's your thought about, from a climate modeling point of view, the different characteristics of the forcing, aerosol forcing versus greenhouse forcing? I know aerosol, if you look at some fundamental processes, aerosol cloud radiation, cloud interactions, aerosol radiation interactions, all kind of that.
Yeah.
Now, but from a feedback point of view, what's your thought about that?
Well, I think, so yes, I agree completely with you that aerosols are regional. It's much more regional. The lifetime of aerosols is a few hours in the vicinity of a cloud and a few days to a week further away from the cloud, near the surface. And so yes, the forcing is concentrated much more closely to near the sources of the aerosols. But it also operates everywhere. And we feel, the studies have suggested that, for example, 20% of the aerosols that are reaching the west coast of the United States are coming from Asia. And so the aerosols do play a role everywhere. And if you especially believe that in places which are not strongly polluted, that the aerosols are very sensitive to small changes in anthropogenic emissions, it could be that anthropogenic emissions are having an effect everywhere. So they're not only local, they can have global impacts as well. In terms of their feedbacks, then I think certainly I think our group is quite interested in understanding how aerosols might be affecting cloud feedbacks, for example, for low and high clouds, and thus acting to modulate the system in ways which we haven't been able to do very much to characterize today in either climate models or in observations, I think. I'm not sure I got to all of your question, Wei Cheng, but very good.
One last question? Sir? Yes.
Hi, I'm a layman on these sort of topics, but also you indicated in your talk and in some recent reports that aerosol could have some effect on deep convection, on extreme rainfall, on the typhoon, hurricanes.
Yeah.
So, how sure are we about we know about this its effect on these extreme events? Or how should we do to have more understanding?
Yeah, well, those are interesting questions from a variety of views. They can operate. The changes in extreme events can operate in a variety of different ways, through both fast responses to the climate system and slow responses. So, for example, if you think that aerosols right now are operating to strongly cool the planet, and then they're keeping SSTs lower than they would be otherwise, then they may be acting to, and that's a slow effect, then because it involves the response of the ocean temperatures, then they could be influencing the frequency of occurrence of typhoons and hurricanes. On the other hand, through their fast effects, through their microphysical effects, then they can operate on fast time scales and change the vigor of convection, and can act both to invigorate and to suppress the convection as well. They're just super complicated. I don't think, at this point, I don't think we can give quantitative answers to those effects at the moment. Thank you all.
Okay. Thank you, Phil.